Good morning, everyone. Today I'm going to read the chapter Fats, Oils, and Detergents. Introduction. Oils and fats are widely distributed in nature, both in animals and plant kingdoms. In animals, they are present under the skin and in muscles, but in plants, they are mainly found in the seeds. Some important examples of fats are butter, lard, tallow, beef, etc., while groundnut oil, cotton seeds oil, olive oil, palm oil, coconut oil, sunflower oil, soybean oil, linseed oil, sesame oil, etc. are important examples of vegetable oils. Fats and oils are one of the three major constituents of our foods, the other two being carbohydrates and proteins. In fact, fats and oils serve as energy reservoirs for the animals. In human beings, only a few hundred grams of glycogen carbohydrate can be stored, which can barely supply the body's energy needs for about 12 to 18 hours. In contrast, large amounts of fats, 12 kg for an average person weighing 70 kg, can be stored, which can supply the body's energy needs for about 8 weeks. Besides this, oils and fats serve as raw materials for a number of industries such as soaps, paints, varnishes, and vanaspati ghee, etc. Natural fats. The fats obtained from the animal sources such as butter from milk of cows and buffaloes, lard from hogs, and tallow from sheep, goats, etc. are known as natural fats. This name is simply given to differentiate the fats from those fats which are obtained by hydrogenation of oils. Edible and non-edible oils. Oils such as groundnut oil, sunflower oil, soybean oil, rapeseed or mustard oil, olive oil, sesame oil, which are used for cooking purposes, are known as edible oils. Which oils such as cotton seeds, linseed oil, castor seed oil, and moa oil, which are used in soaps, paints, varnishes, the lacquer industries, are called non-edible oils or industrial oils. On the basis of the iodine value, oils have been classified as drying, semi-drying, and non-drying oil as discussed. Industrial oils may include essential oils or mineral oils. Essential oils such as rose oil, jasmine oil, lavender oil, eucalyptus oil, peppermint oil, etc. are volatile oils isolated from plants. Essential oils may be hydrocarbons, alcohols, aldehydes, ketones, etc., but not esters of glycerol, etc. For example, peppermint oil, an essential oil, contains methanol, an alcohol, and its chief constituent. Essential oils are mainly used in perfumes, cosmetics, and in pharmaceutical products. On the other hand, mineral oils such as paraffin oil is a mixture of saturated and unsaturated hydrocarbons and not esters or triglycerides. And they cannot be saponified. They are also called oils simply because of their physical appearances. They are non-edible as they are mainly used as fuels. Triglyceride compositions of oils and fats. As stated above, fats and oils are triesters of glycerol with higher aliphatic monocarboxylic acids, that is fatty acids. In other words, they are triacyl glycerols and are commonly as glycerides. Fats and oils can be represented by the general formula given below: triglycerol or triglyceride. Fatty acids. With only a few exceptions, all the monocarboxylic acids isolated from fats and oils are straight chains compounds containing 3 to 18 carbon atoms. Further, with the exception of only 3 carbons or 5 carbon acids, all other acids found in fats and oils contains even number of carbon atoms. The chief saturated fatty acids present in oils and fats are lauric acid, myristic acid, palmitic acid, stearic acid. Besides saturated fatty acids, unsaturated fatty acids containing one or more double bonds in cis orientation may be present in oils and fats. The chief unsaturated fatty acids present in the oils and fats are oleic acid, linoleic acid. Classification of glycerides. The three fatty acids in glycerides may be same or different. Therefore, glycerides are classified as simple or mixed glycerides according as they have the same or different acid residues. For example, simple glycerides, mixed glycerides. Glycerides are further classified into saturated and unsaturated glycerides according to as they contain saturated fatty acid residues or unsaturated fatty acid residues. For example, tristyrene, triolene. Both simple and mixed glycerides are found in natural oils and fats. In fact, oils and fats are complex mixture of mixed glycerides along with small amounts of simple glycerides. Chemical difference between oils and fats. The main difference between oils and fats in the proportion of saturated and unsaturated glycerides. Triglycerides with higher proportions of saturated acid residues such as palmitic acid, stearic acid are solids at ordinary temperature and are called fats, while those with higher proportions of unsaturated acid residues such as oleic acid, linoleic acid are liquids at ordinary temperature are known as oils. Melting points of glycerides. As stated above, fatty acids have one or more double bonds having less stable cis stereochemistry. For example, oleic acid has one cis double bond at C9. Linoleic acid has two double bonds at C9 and C12, while linolenic acid has three cis double bonds at C9, C12, and C15 positions. These cis double bonds have vital biological importance. In the solid state, the molecules of saturated fatty acids fit closely in the crystal lattice due to their size and due to their zigzag tetrahedral structures. On the other hand, cis unsaturated fatty acids have a bend at the double bond and hence do not fit closely, thereby lowering their melting points. Chemical properties. Fats and oils being triesters of glycerol show all the reactions in simple esters. In cases of glycerides contain unsaturated fatty acid residues, they also show the usual addition and oxidation reactions of alkenes. Some important reactions of fats and oils are given below. First, hydrolysis. Fats and oils are readily hydrolyzed by treatment and with superheated steam. Minerals, acids, and alkalis. Fats or oils at 500 Kelvin pressure gives glycerol and fatty acids. Hydrolysis by superheated steam or mineral acid gives a mixture of fatty acids and glycerol. However, when the hydrolysis is carried out by alkalis, glycerol and salts of fatty acids are formed. Since the salts of higher fatty acids and thus formed are used as soaps, and alkaline hydrolysis is commonly called saponification. In the digestive system of human beings and animals, fats and oils are hydrolyzed to glycerol and fatty acids by a number of enzymes called lipases. Second, hydrogenation. Oils which contains a higher proportion of unsaturated glycerides add on hydrogenation in the presence of finely divided nickel as catalyst to form solid fat. For example, triolin is converted into tristyrene. This process is called hydrogenation or hardening of oils. It is similar to the catalytic hydrogenation of alkenes and involves the reduction of double bonds present in unsaturated glycerides to form saturated glycerides. This process is extensively used for the manufacture of vanaspati ghee such as dalda, rat, gagan, etc. from groundnut, peanut, sunflower or other edible oils. Hydrogenation is never carried out to completion but is stopped as soon as the fat of consistency comparable to ghee is obtained. The completely hydrogenated fats are too hard to be useful as kitchen shortenings. The main advantage of hydrogenation is that as compared to oils, fats have a better storage quality. Fats have a better storage qualities and do not become rancid easily. Hydrogenolysis. Third, conversion to alcohols. Fats and oils on treatment with hydrogen at high temperature and pressure and in presence of copper chromite as a catalyst undergoes reductive cleavage to form glycerol and long chain aliphatic alcohols. For example, the splitting of a fat or an oil to glycerol and a higher long chain alcohol by hydrogen is called hydrogenolysis. The long chain alcohols thus produced are used for the manufacture of synthetic detergents. Fourth, trans esterification. Fats and oils can be converted into simple esters of carboxylic acid such as methyl, ethyl esters, etc. by trans esterification. It involves the treatment of the fat or an oil with the large excess of a suitable alcohol in presence of acidic or basic catalyst. The process of trans-esterification is quite useful for the large-scale preparation of long-chain fatty acids and long-chain primary alcohols of high purity. For this purpose, the mixture of methyl esters obtained by trans-esterification is subjected to fractional distillation to separate the individual esters. These upon hydrolysis yield fatty acids of high purity. Alternatively, the individual methyl esters are reduced to get long-chain primarily alcohols. Fifth, addition of halogens. Like alkenes, unsaturated glycerides add halogens across the double bond to form addition products. The addition of iodine is usually carried out by treating the fats or the oils with iodine in presence of mercury chlorides as catalyst. Since the amount of iodine used is proportional to the number of double bonds present, therefore this reaction is used for the determination of extent of unsaturation in a given fat or the oil. Sixth, rancidity. When the fats and oils are exposed to the warm air and moisture for the long time, they develop a disagreeable smell and taste. This process is called the rancidity and involves the hydrolysis of esters to produce fatty acids and the oxidation at double bonds to form short chain acids and aldehydes. These short chain acids and aldehydes are volatile and have offensive smells. Therefore, they impart unpleasant odors to oils and fats. Rancidity is of the following two steps. First, hydrolytic rancidity. This type of rancidity is caused by the liberation of lower fatty acids by hydrolysis of triglycerides. For example, when a butter is exposed to the warm air and moisture, the hydrolysis of the glycerides in butter yields butyric acid and other volatile acids, capric acid, etc., with unpleasant odors. The process of hydrolysis is catalyzed by enzymes lipases, which are provided by the microorganisms present in the air. This type of hydrolytic rancidity can, however, be checked by keeping the butter covered in a refrigerator. Second, oxidative rancidity. This type of rancidity is covered by the oxidation of the unsaturated triglyceride by the air to form short chain acids and aldehydes having unpleasant smell. It is believed that first the esters linkage are hydrolyzed to yield unsaturated acids which undergo oxidation at the site of double bonds to produce short chain acids and aldehydes. Oxidative rancidity can be prevented by addition of a certain chemical, generally phenols, called antioxidants. Two antioxidants which occur in the natural fats are called vitamin C and vitamin E. Analysis of fats and oils. Fats and oils are extensively used in a number of industries. Therefore, it is essential to check the quality of the given fat or an oil. This involves the determination of physical constants such as melting point, specific gravity, refractive index, etc. The chemical constants such as acid value, iodine value, saponification value, Richard Missel value, etc. Some important chemical constants are described below. First, acid value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the free fatty acids present in 1 gram of the fat or an oil. The acid values is determined by dissolving a known weight of the given fat or the oil in a pure neutral alcohol and titrating against standard KOH solution using phenolphthalein as indicator. The acid value is a measure of free acids present in the given fat or oil. A high acid value indicates the given sample of the fat or oil is quite old and has become rancid. Second, saponification value. It is divided by the number of milligrams of potassium hydroxide required to completely saponify 1 gram of fat or oil. In other words, it represents the amount of potassium hydroxide in milligrams required to neutralize the fatty acids formed as a result of complete hydrolysis of 1 gram of the fat or oil. Saponification value is determined by refluxing a weight quantity 1 to 2 gram of the fat or oil with a known excess of standard alcoholic potassium hydroxide solution and then titrating the unreacted alkali against a standard acid. For example, saponification value of trilaureate and tripalmitin can be determined as follows. From the equation, 1 mole of the fat is equal to 3 moles of KOH, or 638 gram of fat is equal to 3 into 56 gram in 3 into 56 into 1000 mg of KOH. Saponification value is equal to 263 mg of KOH per gram of fat. Similarly, for triple methane having molecular weight is equal to 806, saponification value is equal to approx 208. Thus, the saponification value gives the idea about the molecular weight of the fat or the oil. Obviously, smaller the saponification value, higher the molecular weight. For example, triplamethane molecular weight is 806 has the saponification value of 208, whereas trilode with a molecular value of 638 has the saponification value of 263. The saponification value also indicates the length carbon chain of the acid moiety present in the oils and fats. The higher of the saponification value, greater the percentage of short chain fatty acids in the glycerides of the fats and oils. Butter with a short chain fatty acids has saponification value between 210 to 230, whereas soybean oil has saponification values between 189 to 195. Saponification value is used to determine the adulteration of a fat or an oil with some other oil or fat with lower or higher saponification value, or even by some unsaponifiable matter. Third, iodine value. It is divided by the number of the grams of iodine that will be combined with 100 grams of the fat or oil. Iodine value may be determined by one of the following two methods. First, Hubble's method. In this method, a solution of a known weight of the fat or oil in chlorine carbon tetrachloride is allowed to react with a known excess of a standard solution of iodine in ethanol in presence of mercuric chloride as catalyst. The unreacted iodine is then determined by titrating it against standard sodium thiosulfate solution using starch as indicator. For example, the iodine value of a triolin may be calculated as follows. Iodine value of triolin is equal to 86. Second, Viz method. In this method, a solution of the more reactive iodine monochloride in glacial acetic acid is used in place of the iodine and mercuric chloride. A known weight of the oil or fat is dissolved in CHCl3 with solution is then added. ICl adds across the double bond. The ICl left unused is then treated with Ki solution to liberate the equivalent amount of iodine. The liberated iodine is then titrated against the standard hypo solution using the starch as indicator. Iodine value is equal to V1 minus V2 into N into 12.7 divided by W. Iodine value is a measure of the extent of unsaturation present in an oil or fat. Higher the iodine value, more unsaturated is the oil or fat, where V1 is equal to volume of hypo used for Planck titration, V2 is the volume of hypo used for the unreacted ICl, N is equal to normality of the hypo solution, and W is the weight of the oil or fat taken. For example, iodine value of the linseed oil is equal to 170 minus 170 to 185, tung oil is equal to 163 to 171, soybean oil is equal to 127 to 138, sunflower oil is equal to 140 to 156, olive oil is equal to 80 to 100. Fourth, Richard Missel value, RM value. It is defined as the number of the milliliters of 0.1 normal KOH required to neutralize the stream volatile fatty acids obtained by complete hydrolysis of 5 gram of the fat or oil. To determine the RM value, a known weight of the fats or oil is completely saponified with alkali. The resulting solution is acidified with dilute H2SO4 and then subjected to steam distillation. The distillate, which contains the volatile acids, is then titrated against 0.1 normal KOH solution. The RM values is then calculated as follows. RM value is equal to volume of 0.10 normal KOH used for neutralization into 5 divided by weight of the fat or oil taken. RM value is the measure of the volatile fatty acids residues present in a given fat or oil. It is highly useful for testing the purity of butter and desi ghee, which certain a relatively high proportion of glycerides of butyric or other stream volatile acid residues. The RM value of adulterated butter is always lower than that of the pure, 70 to 35. Industrial oils or vegetable origin drying oils. Certain oils such as linseed oil, tung oil, china wood oil, perilla oil, etc., when exposed to the air in thin layers, form hard and tough water insoluble solids. This process is known as drying, and such oils are called drying oils. Oils like olive oil, groundnut oil, etc., which do not dry on exposure to air, are called non-drying oils, and those which dry slowly, such as cotton seed oil, are called semi-drying oils. Chemically, drying oils contain a high percentage of unsaturated glycerides, as shown in their iodine values. On the other hand, non-drying oils have low iodine values, while semi-drying oils have intermediate iodine values. For example, drying oil values have iodine values of 150. Linseed oil iodine oil is equal to 170 to 185. Non-drying oils have iodine values less than 100. Olive oil iodine value 18 to 100, while semi-drying oils have intermediate iodine value. Cotton seed oil iodine value is equal to 105 to 114. Unsaturated glycerides contain linoleic acid and linolenic acid as the unsaturated fatty acid residues. These acids contain 2 or 3 isolated double bonds respectively. In general, drying oils containing saturated glycerides with conjugated double bonds dry more rapidly than those containing isolated double bonds. Drying oils are used as a medium for paints, varnishes, as lacquers. In fact, paints and suspensions of some pigments or the organic coloring matters in linseed oils, to which some turpentine oils has been added as a thinner, When these paints are applied on any wood or iron surface in the thin layer, they quickly dry up to form a tough organic film which protects the surface being painted. Mechanism: the actual process of drying does not simply involve removal of moisture or evaporation of solvent but involves complex changes. It is believed that the reactive allylic hydrogen present on the carbon next to the double bond present in unsaturated glycerides are first attacked by the oxygen to form hydroperoxy compounds, which then combine with the allylic hydrogen on the other glyceride molecules, forming peroxide bridges. The monomers molecules thus obtained subsequently undergo polymerization to form a tough network solid. The whole process is sketched below. Soaps. The substances like soaps and synthetic detergents which concentrate on the surface of the solution or interfaces form surface films, reduces surface tension on the solution and help them removing dirt and dust by emulsifying grease are called surface active agents and surfactants. The molecules of the surfactants contains two characteristic groups, one of which is water soluble and the other is oil soluble, that is known as lipophilic. Soaps are sodium or potassium salts of higher fatty acids such as palmitic acid, stearic acid, or oleic acid. These soaps are generally obtained by the hydrolysis of oils and fats with aqueous alkalis. The process is known as saponification of oils and fats. The fats and oils commonly used for soaps manufacture are tallow, lard, olive oil, linseed oil, mava oil, rapeseed oil, coconut oil, and palm oil. Soaps containing 12 to 18 chain atoms have good cleansing action. Soaps with 12 carbon atoms are comparatively soluble in water, whereas soaps containing 18 to 22 carbon atoms are not useful as soaps because of their insolubility in water. Sodium soaps are generally hard and hence are called hard soaps. These are used for washing of clothes. Potassium soaps, on the other hand, are more expensive and produces a softer lather and hence are called soft soaps. They are used for making shaving creams, shampoos, liquid soaps, etc. Transparent soaps are prepared by dissolving ordinary soaps in alcohols and removing the insoluble parts by filtration. Evaporation of alcohol leaves behind transparent mass. Soaps are 100% biodegradable, that is, microorganisms present in the sewage water can comparatively oxidize soaps into CO2. As a result, it does not create any pollution problems. However, soaps have two disadvantages. First, soap cannot be used in hard water since calcium and magnesium ions present in the hard water produce curdy white precipitates of calcium and magnesium soaps. Second, soaps cannot be used in acidic solutions since acid present in the solution precipitates the insoluble free fats acid which adhere to the fabrics and thus block the ability of the soap to remove oil and grease from the fabrics. Synthetic detergents. These days, in place of soaps, the substances which are being largely used in cleansing agents are known as synthetic detergents. As the name suggests, they are obtained from purely synthetic chemicals as compared to soaps which are derived from chemicals which are obtained from natural sources like oils and fats. In fact, synthetic detergents are sodium and potassium salts of long chain alkyl hydrogen sulfates or aryl sulfonic acids. Unlike soap, synthetic detergents can also be used conveniently used in hard water. This is due to the reason that calcium and magnesium salts of detergents like their sodium and potassium salts are also soluble in water. Hence, synthetic detergents do not form curdy white precipitates with hard water. Further, they can also be used in acidic solutions. However, synthetic detergents have one disadvantage. Like soaps, they are not completely biodegradable and hence cause water pollution. Synthetic drugs are of following three types. First, anionic detergents. These are so called because a large part of their molecules are anions. These are of two types. A. Alkyl sulfates. They are obtained from the long chains alcohols by treatment with concentrated H2SO4 followed by neutralization with NaOH. Some important examples of this type of detergents are sodium lauryl sulfate and sodium stearyl sulfate. Sodium lauryl sulfate is also called sodium dodecyl sulfate and is used in shampoos and cosmetics. These sodium alkyl sulfates are 100% biodegradable. These are also effective in slightly acidic solutions since they form an alkyl hydrogen sulfate which is a soluble material, whereas soaps react with acidic solutions to form insoluble fatty acids. B. Alkyl benzene sulfonates. These are obtained by conversion of benzene into long chains alkyl benzenes followed by sulfonation and neutralization with NaOH. The most widely used domestic detergents in the sodium P and deodecyl benzene sulfonate. It is prepared as follows: benzene in presence of CH3, CH210, COCl, anhydride AlCl3. Friedel-Crafts acylation gives and dodecanoyl benzoyl, and then Clemention's reduction is seen. Another important example is sodium 2-dodecyl benzene sulfonate. Alkyl benzene sulfonates, in which the phenyl group is either attached to the end of the chain, long alkyl chain, or any other secondary positions, have high biodegradability and hence are called soft detergents, while alkyl benzene sulfonates have branched chains. Alkyl groups have poor biodegradability and hence called hard detergents. To differentiate these detergents on the basis of biodegradability, alkyl benzene sulfonates have long straight chains such as sodium P and dodecyl benzene sulfonate, and sodium 2-dodecyl benzene sulfonate are called LAS detergents, linear alkyl sulfonates, while those having branched chains are called ABS detergents, alkyl benzene sulfonates. An important example of ABS detergents is hard or non-biodegradable ABS salts. It is prepared by Friedel-Crafts reaction of tetramer of propylene with benzene followed by sulfonation and neutralization with alkali. Second, cationic detergents. These are quaternary ammonium salts, chlorides, bromides, acetates, etc. containing one or more long chain alkyl groups. These are also called invert soaps because their surface activity is due to the positive ion and not a negative ion, as in the alkyl hydrogen sulfate detergents. Being more expensive than the ionic detergents, they find limited use. Besides being good cleansing agents, they possess germicidal properties and therefore they are widely used as germicides in hospitals. Third, non-ionic detergents. These are esters of high molecular mass alcohols obtained by reaction between polyethylene glycol and stearic acid. These may also be obtained from long chain alcohols by treatment with excess of ethylene oxide in presence of a base, like alkyl sulfates, ethoxylates, and also biodegradable. Hydrogen bonding in numerous oxygen atoms make the polyether end of the molecule water soluble. Alternatively, the ethoxylates can be converted into sulfates and used in form of their sodium salts. Some liquid dishwashing detergents are of non-ionic type. Composition of a detergent cake. A cake of detergent contains about 20% of active detergent and an equal amount of sodium sulfate to make up a bulk of the powder. A further 30 to 50% of sodium tripolyphosphate Na5P3O11 or STPP is added as an additive. In coordinates with calcium 2 positive and magnesium 2 positive ions present in hard water and thus enhances the cleansing efficiency of the detergent. Other ingredients include sodium perborate, which acts as the bleaching agent, some optical brighteners and fluorescers, that is organic compounds which make yellow clothes appear white, and some foaming agents. Detergent pollution. Detergent having branched chain hydrocarbon chains cause pollution in rivers and other waterways. The reason being that side chain stop bacteria from attacking and breaking the chains. This results in slow degradation of detergent molecules leading to their accumulation. Since the unbranched chains are more prone to attack the bacteria, therefore in most of the detergent used these days the branching is kept a minimum so that the detergents become easily biodegradable and pollution is prevented. The second serious environmental problem is caused by the phosphate additives, that is STPP, which are discharged into the rivers and lakes from the sewage system. As such, phosphate is not a pollutant but is actually a fertilizer. This excess of phosphates promote the growth of the water plant, which in turn deplete the water of available oxygen for fish and other aquatic animals. As a result of want of oxygen, water animals die and rot. In other words, lakes become full of dead animals and vegetation, and hence ceases to act as a source of potable water. In view of these environmental hazards, government of many countries have passed a law to reduce the use of phosphate additives in detergents to mitigate The source of pollution. Cleansing action of soaps and detergents. All the soaps and detergents contains two characteristic groups, that is a water soluble hydrophilic group and an oil soluble lyophilic or lipophilic group. As a result, one of the end of the molecules of a soap or detergent tends to go into the oil phase and the other end tends to go into the water phase, and the net result that the material soap or detergent concentrates at the surface of the solution or interferes. The dirt is generally held to a dirty surface by a thin film of an oil or grease. When the dirty surface is treated with soap solution, the nonpolar hydrocarbon chain of the soap or detergent dissolves in the oil or grease, and the carboxylic group of the soap or the sulfonate group of the synthetic detergent is held by surrounding water. This lowers the surface tension between the water and the grease. As a result, a stable emulsion of the oil in water is formed. When the surface of the cloth is mechanically scrubbed, the loosened dirt particles are adsorbed by colloidal soaps or detergent particles and ultimately washed away. Thank you.